Hey everybody, welcome back to our second video in the nephron transporter series. So now we're going to talk about the second portion of the nephron after it's filtered. First, it's going to go to the proximal convoluted tubule, and then it's going to go to an area called the loop of Henle. So I've highlighted the area in green at the bottom of our slide here. So you can see the yellow portion was our proximal convoluted tubule, and now this whole portion right here is our loop of Henle. So as you can see, the loop of Henle is a pretty long portion of the nephron, and I like to break it up into two parts so that you're able to compare and contrast these portions. So the first part that we have is what's called the thin descending limb of the loop of Henle, and then coming back up, there is the thick ascending limb of the loop of Henle. Technically, there is also a thin ascending portion of the loop of Henle, but really the area that you want to focus on in terms of your physiology and your pharmacology is the thick ascending loop of Henle. So if we first look at the thin descending portion of the loop of Henle, I want you to notice a couple key things. First, highlighted in orange, I've put that H2O is passively reabsorbed, and this is driven by medullary hypertonicity. So what do I mean by that? To really fully understand this concept, we have to actually look at the other section of the nephron as well, the thick ascending limb, which we will do in a moment. But when I say hypertonicity, I mean that there is a bunch of solute in the medullary space that is actually pulling the water out. Remember our principle of osmosis. Let's say we have a bunch of solute out here. The principle of osmosis tells us that water is going to flow from area of low solute concentration to high solute concentration. So you would expect to see the water come out here if there was a lot more solid in the medullary space. So that's what I mean by hypertonicity of the medullary space. Another really important thing here is this impermeability to sodium. Why does this matter? Because you can see as we move down thin descending limb, look at the concentration of our solute, 300, 700, 1000. So you can clearly see this becoming more and more concentrated because we are both passively reabsorbing water in H2O, but this impermeability of the cells, this inability to bring out sodium, creates a system that allows us to get more and more concentrated as we move down. We're reabsorbing water, but we're not able to reabsorb the solute. So if we're just able to reabsorb water in this portion of the nephron, but not actually reabsorb the solute, that should make sense as to why we're getting more and more concentrated as we move our way down the thin descending limb of the loop of Henle. So that explains our last point, which is that the thin descending loop of Henle acts to concentrate the urine and create a hypertonic state. Hypertonic meaning that there is a lot of solute in it relative to the amount of water. Next, let's turn our attention to the thick ascending loop of Henle. This is where a lot of the transporters are that we need to know. This is where a lot of our pharmacologic interventions work. And you'll notice as we talk about this, there are a lot of things that essentially are the opposite of what the thin descending limb did. The first point is that there's actively reabsorbed sodium, chloride, and potassium in this portion of the nephron. Remember we said in the thin descending limb that sodium chloride, it was impermeable, so it was unable to be taken out. This is the opposite, where we actually have permeability to the sodium chloride, which is what allows us to make this concentration gradient that we talked about. We said there's a concentration gradient in the medullary space, so this area right here, where solute is pumped out, the sodium chloride is pumped out, which allows water to be drawn in through the principle of osmosis from the descending portion of the loop of Henle. So one of the main things that you guys need to know is the way that this occurs, the way that the body does this, is through something called NKCC transporters. So let's draw our attention over here to this diagram, and as you can see, we have the NKCC transporter right here. So NKCC essentially is one letter for each ion that's absorbed. The N is for the sodium, the K is for potassium, and the CC is for two chloride ions that come along with that transporter. This is a very interesting transporter in terms of its mechanism in that it undergoes something called secondary active transport. So remember when we talked about the classic sodium potassium ATPase, this is primary active transport where an ATP molecule is actually pushing these molecules to go against their concentration gradient. So it's pushing sodium out of the cell, even though there is more sodium outside of the cell already. So it's having to work against the concentration gradient. Vice versa, we know that at baseline, there's a lot of potassium in the cell. And so the ATP is really helping to push this potassium here against its concentration gradient. This is a different mechanism than the NKCC transporter, which is undergoing secondary active transport, where it is essentially using the sodium's concentration gradient to be pumped across the cell and bringing other ions along with it. So the sodium potassium pump on the basolateral membrane, which is actively pumping sodium out of the cell into our bloodstream, is essentially creating less sodium in the cell, and thus on the apical side of the cell, the sodium can actually be moving down its concentration gradient into that cell. So the NKCC channel is essentially using a concentration gradient to bring sodium and other ions back into the cell. Notice it's bringing one sodium and one potassium, which are two positively charged ions, along with two chloride, which are negatively charged ions. So you're bringing two positives and two negatives, and thus you're keeping electrochemical neutrality. So then if sodium is pumped into the cell, water must follow, because the principle of osmosis says that water is going to go from low solute to high solute. And typically that would be true, but here it's actually not. And the reason is because in the thick ascending loop of Henle, it's impermeable to H2O. So we're bringing across sodium, but we're unable, or the body is unable to reabsorb that water with it, which is part of what helps create less concentrated urine. We can see over here that sodium chloride is going from inside of the tubule, inside of the nephron, into the medullary space. And remember our terminology here, if we're taking a substance out of the nephron into the blood, the peritubular capillaries, that's called reabsorption. However, because we can't also bring back water on this side of the nephron, you see that we get less and less concentrated as we move up the ascending limb, because we're actively bringing back solute, but overall that's going to dilute what is actually left in the nephron. We're taking out the salt, but we're leaving the water behind, creating a dilution of the fluid that remains in the tubule, which ultimately leads to dilute urine, or hypotonic. Hypotonic meaning that there's low solute relative to the amount of water. So remember, again, we have to be able to compare and contrast the descending limb with the ascending limb. Remember, as we go down the descending limb and water is passively reabsorbed, we are creating a hypertonic fluid in the tubule. We're getting more and more concentrated, which is the opposite of what happens on the other side of the loop of Henle. As we go up the ascending limb and sodium is continuously pumped out, we are creating more hypotonic urine. That means that it's less concentrated as we move up the ascending limb. And the final important thing for us to talk about with the thick ascending loop of Henle is this idea of paracellular reabsorption of the magnesium and the calcium. So we can recognize that magnesium and calcium are very important ions and molecules for our body, right? Magnesium is used in a lot of chemical reactions. Calcium is used as well, and it's also a big component of our bones. However, these are larger molecules, and they also have a positive charge, a 2+ positive charge, which makes it really challenging for them to make their way through the cell without an actual transporter involved. As you can see by looking at the diagram, there's not a transporter available that would make it easy for us to bring calcium and magnesium through the cell and back into our body. And so we have essentially developed ways over time to bypass this. Instead of going intracellularly, intra meaning within the cell, we go paracellularly. So we go around the cell. So how does this process work? How does our body take advantage of electrochemical gradients and electrochemical potential to create this process? So as you can see, if we look at our magnesium and calcium molecules, they are actually going between the cells in this concept of paracellular transport. So the question is, how or why does this work? And the answer lies within taking advantage of electrochemical gradients. So remember, with our sodium potassium pump, we are consistently pumping potassium inside the cell. There's a ton of potassium inside the cell because of this pump at baseline. As you can see on the apical side, or the side of the cell that is facing the lumen of the nephron, we have a potassium channel that allows potassium to freely go down its concentration gradient. When I say down its concentration gradient, I mean there is a lot of potassium in the cell, I'm drawing with a big K, and there is much less potassium out here. So naturally, if given the opportunity, if a channel is available and hey, here's a channel available, potassium will go down its concentration gradient. Think about it like if you're riding a bus and it's super crammed and you just can't wait to get off the bus. That's how potassium feels when it's stuck inside the cell with all the other potassium molecules. If you give it the opportunity, if you open the bus doors, potassium's going to get off the bus as quickly as possible, or it's going to leave the cell as quickly as possible. So if we understand that potassium is moving down its concentration gradient, then we have to think about the next step is what are the other effects that happen. If potassium moves down, we move a bunch of positive charge into the lumen of the nephron. What is that going to do to other molecules? And the answer is it creates a positive propulsion. If we put two positive charges together, what are they going to do? They're going to repel each other. So the same principles are occurring here, right? If we have a bunch of potassium with a bunch of magnesium and calcium over here, these are a bunch of positively charged ions. What are they going to do? They're going to push each other away. They're going to repel each other, just as two positive magnets would. So taking advantage of this principle explains how we're able to have this concept of paracellular transport. Potassium is pumped out into the lumen right here, where the magnesium and calcium is, and that repulsion of the positive charges is what pushes the magnesium and the calcium paracellularly, or between the cells, and allows our body to reabsorb some of it. So just as a general recap to make sure you guys understand the high importance points here, is that the thin descending loop of Henle and the thick ascending loop of Henle work together to concentrate and dilute our urine and allow the body to bring back sodium chloride and the water that we need. So in summary, to make sure you guys really understand the big picture here, you want to be able to compare and contrast the thin descending limb with the thick ascending limb. Notice we said that one's passively reabsorbing water, the other is actively reabsorbing sodium and chloride. This is working together. Bringing back the sodium chloride actively in secondary active transport is creating a gradient that is allowing us to reabsorb H2O on the other side of the loop of Henle. The reason that we don't reabsorb water on the same side of the loop of Henle that we're bringing back the sodium chloride in is because that portion of the loop of Henle is actually impermeable to water. So the thick ascending limb is impermeable to water, whereas the thin descending limb is permeable to water. So our body takes advantage of these opposite mechanisms on the different sides of the loop of Henle. So I think that's one of the key points of this video, is to understand that. The second key point is to understand paracellular reabsorption. And again, we just said that potassium leaks out through this channel right here. This creates a bunch of positive charge in the nephron lumen, which is going to push the magnesium and calcium between the cells, or paracellularly, to help us reabsorb some of those important molecules. And the final thing we're going to talk about for this video is a genetic condition associated with damage to the NKCC channel, and that is Bartter syndrome. So notice Bartter syndrome is a reabsorption defect of the NKCC channel, which we talked about already. It's similar to the use of loop diuretics. So if you haven't seen our pharmacology section, I recommend you check that out to learn about loop diuretics. But essentially the primary mechanism of a loop diuretic, such as furosemide, is to actually inhibit the NKCC channel and thus block our ability to reabsorb the sodium, the potassium, and the chloride in the loop of Henle. This creates a variety of different exam findings, such as metabolic alkalosis, low calcium, and low potassium. This should make sense, right? If our NKCC channel is not working, we're not bringing back our potassium as well as we normally could. That's why we get low potassium levels. If we're not bringing back our potassium and we don't create this high concentration gradient of potassium inside the cell, not as much of it is going to leak out through this potassium channel. If that doesn't occur, we're not going to create that electrochemical gradient, that positive ion charge that's going to push calcium and magnesium paracellularly. And that is why we end up having low calcium levels, because we're not reabsorbing as much of it because of the defect of the NKCC channel. And finally, this idea of a metabolic alkalosis occurs because, again, if this channel is not working, right, if this channel is out of commission, we're not bringing back a very important molecule in our sodium. If we don't bring back our sodium, we're not going to get that osmosis effect where we bring back our water. Additionally, as that sodium moves downstream in the nephron, it goes from the loop of Henle to the distal convoluted tubule and ultimately the collecting duct. This is going to stimulate a system in the body, which we will talk much more about in the next chapter, called the RAS system, which works to actively reabsorb sodium at the expense of excreting hydrogen protons. So two things are happening. We're losing our salt, and thus we're losing some of our water volume, because if we don't reabsorb our salt, we're not going to reabsorb our water. And we're excreting more protons at a later portion of the nephron, we will talk about in an upcoming chapter. And because of that, we are creating an alkalotic state. And the final thing they want you to know is the genetic inheritance pattern, which is autosomal recessive for Bartter syndrome. Remember, most of the nephron genetic pathologies are autosomal recessive. The one that's different and unique is called Little syndrome, which is autosomal dominant. We'll talk more about that when we talk about the collecting duct. And so I tend to think a good memorization technique or a good strategy is to remember the one that's unique, which is Little syndrome, is autosomal dominant, and then all of the rest of them regarding renal tubular genetic conditions are autosomal recessive. That way you just have to memorize one, and then all the other ones can be categorized into one big group. All right, so that was a lot in this video. Go ahead and watch it again if you need to. The main points to recap here is to compare and contrast the thin descending limb with the thick ascending limb. Think about the transporters that are used. We are reabsorbing sodium on one side so that on the other side we can reabsorb the water. Why do we have to do this on separate sides? Because on one side it's impermeable to sodium and on the other side it's impermeable to water. So we are working together to help reabsorb the important molecules and nutrients that we need, as well as maintain our volume status. Additionally, we are taking advantage of electrochemical gradients to reabsorb other molecules, magnesium and calcium in this case, that our body needs to reabsorb. We need for a variety of reasons, but we don't have actual transporters to do them. So our body is creative and it takes advantage of potassium moving across the cell to create a repulsion of other positively charged molecules, namely magnesium and calcium, so that we can reabsorb those in a different mechanism.